So now what we can do is we can use these decompositions to resynthesize magnitude spectrograms and then eventually audio using activations and bases that are mismatched with each other. So this idea of taking the activation from the snare, but the basis from the hi-hat, and then getting a basis of a hi-hat, a spectral template of a hi-hat that's being activated by the rhythm, essentially, of the snare. In order to do that, the first thing I've done is I've actually taken the script from the first two videos and cleaned it up a little bit so that it's a little bit more manageable, broke some things out into some functions, and also created a function that will save the decomposition to a JSON file. And so what we're giving in here is, a path of where we got this audio from, the sound file, the number of components that we decompose it into, the bases, the activations that we got from our decomposition process, and then our FFT settings. So when we do some resynthesis, we can know what the FFT settings are. And this function here will basically just pack them all into a object and then write it out as a JSON file. So let's do that, and then we can see what that decomposition JSON file looks like. So from here, I can call Python NMF decomposition. Let's just see what we have to provide here. Audio path. I'm going to use the Nicole drum loop again still. And then end components will be 3. And then there are some options here. I could specify to only read in a certain number of seconds of the sound file. I could set a Boolean flag to plot if I wanted to see the plot. I'm not going to do that now, but it's the plots that we were looking at in the last videos. And then also a flag I could set to do the resynthesis on these components right here in this moment. And so this won't do the sort of cross synthesis with mismatched activation and bases. This will just recreate the components as Flucoma does. And this will do it with the masking strategy that we looked at in the last video. So there will be the good sounding version, and we'll do that. Audio path is misspelled. So now if we go check this, we'll see that we have our components. As we would expect them. And also there is a Nicole loop E dash decomposition JSON. What we can see here is we have some information, how many components, the FFT size, the hop length, the sample rate of the original sound file, where that original audio path came from. It's relative, so we have to make sure we're staying in the same folder here. And then the activations, as well as the bases that we would need to do the resynthesis. Now this file is 140 kilobytes, which is really not large at all. So we're able to essentially compress the information from the sound file to be able to resynthesize it down into just 140 kilobytes here. So then what we can do is we can use this file and load it into a resynthesis script to do the resynthesis, and we could do it using matched activation and bases. Of course, we've already done that because it's sort of built into this script right here. While we have that information in memory, it makes sense to just do the resynthesis if we want to. But here we could load in that file and then resynthesize audio using mismatched activations and bases either from the same sound file, or we could even load in 2 different JSON files from 2 different decomposition files and use a basis from one sound file decomposition and activation from another sound file decomposition. So there's a lot of creative possibilities that this could open up. So let's do that. So the way that this is put together is that we're going to pass in a JSON file that will contain the decomposition information that we want to draw our bases information from. And then we'll need to pass in a basis index. So in our bases JSON file, in our JSON file that contains the basis information we want to use, which basis are we going to use? And then the same for the activations, a JSON file that will contain the decomposition from which we're going to draw our activation information, and then an index, which activation should we use from that decomposition, and then an output path about where to save our resynthesized audio. So the first thing we're going to have to do is we're going to have to load in these JSON files and get them into objects. With the bases data file, read, load in the JSON file, and this is now our bases data. Do the same with the activations data. And then from those, get the bases and activation information that we'll use to do the resynthesis. So we'll say basis equals bases data at the bases index. Activations data at the AX. I think that's what it's called. Let's go double check. What do we call it? We called it AX. Okay, great. The activation index. And then we can do our outer products to get our resynthesized magnitude spectrogram. And to make sure we're doing this right, let's print the size of that and see what it looks like. So we'll just see if this is going to give us what we're expecting it to give us, and we'll call this. So now what we'll say is NMF resynth. Bases data will be our Nicole decomposition. Activations data will be our Nicole decomposition. Basis index will be 0. Activation index will be 0. So here we're not doing a mismatched basis and activation. We'll just see if this is going to give us what we want. Following arguments are required. Yes, outpath. Okay. So now we have something that is 513 magnitudes tall and 887 activation, or I should say FFT frames long. So this is the proper matrix shape that we were hoping for. So then we can take this and combine it with phases to get our resynthesized STFT. What we could do is we could find some original phases to combine with this in an inverse STFT. It might make sense to use the phases from the activations decomposition because we would need them to be the same length, the same number of FFT frames as we have in this resynthesized magnitudes, which we will get from the length of our activations data here. But we're already potentially doing a mismatch between activations and bases, so we're not going to try to recover some old phases because I'm not sure that that's really going to be a plausible solution. Instead, what we'll do is we'll use a function from Labrosa, which will take our resynthesized magnitudes, generate some plausible phases for it, and then return to us audio using those plausible phases with an inverse STFT. And that process is called the Griffin-Lim algorithm. So now if we look and see what this Y is, it tells us that it's about 200,000 samples long. So this is now our audio that we have. So now what we can do is we can take that audio and write it to disk. We'll take the sample rate from our bases information. We might want to check and make sure that our sample rate from our activations data and our bases data are the same. I think it'll be okay if we don't do that. And now if we go listen to that file, which I called test.wave, we hear that it is only 5 seconds long and it sounds like it's playing back very quickly, which means we probably have the wrong hop size or FFT settings information provided. So let's go back here and see if we say hop length equals bases data hop length. Let's do that. Yes, but let's actually change it to activations data. I think this will be better because that's really how we're organizing through time is we're getting the length of the resulting sound file here by the number of FFT frames in the decomposition, and the number of FFT frames are really coming from our activations, not our basis, right? So let's do that. Cool. So now what we can do is we can use the rhythm. So these are the original, these are the components that I resynthesized from the initial decomposition. So these are not the mismatched activations and bases. So if we take the rhythm or the activations from component 0, and then the basis of the snare here in component 1, we should be able to resynthesize these two and get the spectrum of the snare playing the rhythm of the kick. So activations will be 0 and basis will be 1. Not bad. So you can see it doesn't sound quite as good as the decomposition where we have the same activation and basis, partly because it really doesn't make sense to use a masking strategy here. The masks are only useful when you have the original spectrogram that are going to have the same sound objects in the same places in spectrum and in time. So we can actually mask that original to let those elements come through. So even if we were trying to mask the original magnitude spectrogram, it's really not going to turn out the way that we might think it would. Okay, let's try a couple more. Some of that spectral stutteriness in there. Not bad. Also not bad. And then let's do one where we have things from different files. So first we'll again do a NMF decomposition, and we'll get the audio from this piano file. So we'll also do 3 components because it has those 3 piano hits. Let's make sure that our decomposition script here is loading mono. Good, okay, because that's a stereo sound file. And then I think we should be good. And now we should have a Nicole decomposition JSON and this Tremblay SA upright decomposition JSON. So now all we have to do is say resynth, and let's use the bases from the piano so we get that piano sound. We can just say bases data should be that JSON, great. Activations data, the Nicole. And for this, I mean, we could just say basis index 0, activation index 0, because this is going to be a mismatched basis and activations anyways. And now we have that done. Let's listen to it. So there you go. So, you know, again, it's not the greatest sound. There's some like spectral artifacts in there. The results tend to be darker, like the upper frequencies tend to not be as present. But there's a lot of possibilities that this opens up, and it probably will make some cool sounds. So